Let's begin. First of all, I'd like to thank my colleague Peter Carlson for inviting me to speak about FEM design and structural analysis. I know you're all impact users, but I want to know how many of you also work with structural design? Good. Because my presentation will be almost all about that. My name is Dennis, and I'm head of Strusoft Denmark. And besides the managing of Strusoft Denmark, I also am very much involved with the sales of especially our structural analysis software, which means FEM design, dimension, and WinStatic. And I'm also part of the development of FEM design, so if you have any good ideas, also come to me afterwards. And FEM design is very focused on prefab structures, which I assume that everybody in here likes. So let's begin. I have put up some points. Workflow about Impact Revit. You all saw this nice presentation of Desi, and this is going to be the future. So this is something that we're really concerned about, how this workflow should work between the structural engineer and the impact and also back. So how do we make this circle close the BIM circle, also in precast? So we have the workflow. We also have the workflow between AutoCAD and FEM design. Many of you may not know that we can do this already. Then we have some case studies from the top kingdom in Scandinavia. It was not a joke. Then we have some examples of wall design, and I will show you some example of the stringer panel method, which is a method that is very widely used in Denmark. First, you might recognize a little bit of this model. I got it from my colleague Desi. And I told her, can you please send me a Revit model, a Revit impact model? And she sent me the model over there. It's not that complicated, it's very small, but it has a lot of objects. And what I did with this model, I opened it in my Revit. And I activated the FEM design add-on to Revit. And I could see that many of these lines were not in place. Revit has this functionality here. You see the red dots, the green dots. The red dots are points that are not connected to anything else. The green dots shows that it's connected to the neighbor regions. It didn't look like this when I opened it. They were all red. But we made a tool in Revit, a plugin that helped us adjust these lines, so we're sure that the walls like here intersect in the right points, that we don't have two different planes not meeting each other. And this is important if you're going to do structural analysis in a finite element software. It must be correctly connected. So this is important stuff. But it's easy to do. Revit has amazing tools for it now. It didn't have 2 years ago. We made our own plugin to make it even more easier. And we have videos on YouTube showing if you spend 10 minutes on this, you will be able to do it. So this is our dream, to make a connection between your impact models, whether it's in Revit or in AutoCAD, doesn't matter, with the structural engineer. When I took it to FEM design, it looked like this. So what you see on the left is we have a model, we have some vertical load, and we have some horizontal load coming from the right side towards the left side. And we can see the compression zones in the bottom of each wall. You can see it with kilonewton per meter, or you can just see it like this, which we often prefer. We did this in a collaboration with a Danish company, and they said that they were tired of all this kilonewton per meter or stresses and colors. We want to know if we put 100 kilonewton in wind load, I want to see that 10 goes into this wall, 10, 10, 20, 20. Easy. I need to get an overview of all these colors. So we made this. So now that we have it, the impact model in FEM design, we have put on the loadings. The next natural step will be our reinforcement design. FEM design designs the reinforcement for you and it optimizes it. And it can go very far, but you can design how exact you want it to be, how much on the safe side you would like it to be. And the FEM design we are releasing in the new year in January will have also the buckling effect of the wall. It will have plastic regions, plastic connections, in Danish fuge. I don't know what the name is in English, but we will have all our joints will work plastic with equal distribution of the internal forces, which will also optimize our reinforcement design. All this can of course also be done for the thing you have today, which most probably is the AutoCAD version. You can take an AutoCAD file into our FEM design, then you can just click on the corners of each walls and on the openings, and you don't have to put in the coordinates again. So you can reuse, that's the old BIM. Reuse of drawings to create new models. A little bit of BIM case stories. This is on the harbor in Aarhus in Denmark. And was built some years ago, but they were pioneers in this. And it's made by a company called Niras. And they got this Revit model at the left. That was where they started. They got it from the architect. And then they took all the architectural members, architectural walls, and turned them into structural in Revit. And you can see the blue, which looks like like a ghost city or something like that. But all the blue is the structural elements, which means the elements that helps carry the loadings. Then we have a mapping function. We need to translate from Revit language into FEM design language. And in Revit, you can call material whatever you like. So we had an example here called BIPS concrete in situ beton plastøbt. So we need to tell that this material in Revit corresponds to this material in FEM design. So it's like a dictionary. And this we need to do to make sure we don't get a Google Translate function. So we need to control manually how is this translated. And what did they gain? They gained immediately a full overview of their forces on the foundations. In this, they could determine in the early state if they needed anchors on the building. This is what they are up to, because this is what they're going to build the first. That's the foundation. So they got an overview of all their reaction forces. They got all their forces down in the walls. You see horizontal force, vertical force, rotational moment. So they could have a good overview of, is this model working like we want it to work? So real simple. And then another feature they found out. Then now they could test the forces in the joints, the shear force in the joints, the vertical shear force in the joints. Whether you have these the regular stirrups or you have the wire box, they will have two different load carrying capacities, and this is something we need to be aware of. If we want to link this wall to this wall because we need its weight in the stability system, we need to make sure that this load is less than the capacity. So suddenly they got full overview of all their loads in the joints as well. Another project, if you come to the capital of Scandinavia someday, you will see this beautiful building. It's the University of Copenhagen, made by Ramboll. They designed it, also a FEM design project. And something I know that you here in Sweden love, that is the Carlsberg. So I brought this example for you guys. Carlsberg left Copenhagen. They want to produce it somewhere else, Asia. But they left a very nice building site in Copenhagen. So they are building a lot of stuff, and most of it is actually designed in FEM design. This is one of the examples where you have the building at the left, and then they're building the tower in the corner of the building. So it's two separate models, but in real life they are linked together. And it's also made by Ramboll, the tower and the calculated stability and all the load takedowns. Yeah, then we have another project, Axel Toe. I actually brought it because I know we have many precasters here today. And I would like to share a story, what happened when this project drawing came into the offices of the precasters. Our entrepreneurs, the big contractors, they panicked a little bit. And I went to some meetings and I saw drawings of this in hollow core slabs. That was the most amazing thing I ever saw. And I had courses in 2 of these contractors, and both were calculating offers for this project. And they were panicking. So they made beams everywhere, slabs everywhere. It was so chaotic. And they had to cast the edge in situ. In situ, we don't use that word in Denmark anymore. It's only precast. So what happened was our 2 Danish contractors, they were so expensive that the building owner could not afford it. But then Syblin from Germany came with this brilliant idea. We do it in situ. And we were shocked. In situ. This was just a funny story to show you. We also do a little bit in situ still in Denmark. A case study of how they designed the precast walls is from Mo. We focus a lot on this in Denmark. How do we optimize our structural designs of walls like this? Because the architects, they love to make holes in our walls. And they would love to put them like this everywhere. They don't do it like this anymore. It's history. So now we cannot calculate our pillars going all the way down. We need to move the forces around the corners of the window openings and door holes, and it's a pain in the ass. But we love it in the software industry. So, what we do now, when they removed all the walls in the length direction of the building, we need to activate the facades, and they often look like this. It's chaotic. So this FEM design is widely used for this, to design these openings, to make sure that your openings, your edges, your corners can take this force that it needs to take for calculating stability like this. So, and the hollow core slabs, this is a model for a design of hollow core slabs. This is how we do it in Denmark. We calculate the hollow core slabs can only take shear, and then we have our reinforcement on the edges and in between the hollow core slabs taking compression and tension. We call it the stringer panel method. We do this all the time. So that's a completely normal way to do it. And you see the forces in the edge reinforcement here in kilonewtons, and you can design your edge reinforcement. So it's like when you design a concrete beam, you have a compression zone, you have a tension zone, and you have this shear in between. This is how we calculate everything. So we call it the stringer panel method. The last thing I would like to share with you here is our new software that works with impact models. So you take your walls from your impact, you take it to our new software called the stringer software, and this is the external geometry. The software now moves these stringer bars 10 centimeters in from all edges, because we know we cannot place reinforcement inside the walls on the edge of the walls. We need to have it inside the wall. And it takes time to sit and measure 10 centimeters, 20 centimeters. So we've made a function that draws it automatically for you. And then you get the one you have here in the left is the shear force in the panels, in the hollow core panels. And of course, the joints in between the hollow core panels should be able to take this load. We have a check of that as well. So you have the panel forces, you have the reinforcement forces, the edge, the stringer forces here. And you have, of course, the Eurocode check of how much utilization you have of each hollow core shear field. And this method can be used both for walls, for slabs, for anything. And then we have the code check here. So this software will be released hopefully in the beginning of March. We are testing now. So, and we just managed to connect it to Impact like 2 or 3 weeks ago. So this will be nice. Mark your elements in Impact, take it over here, add the loadings, design your walls. That's it. So thank you for inviting me and giving me the opportunity to talk about the structural engineering. I think after this there will be lunch, but let's take the questions first. I'm sure you have a lot of questions. No questions about the prime capital of Scandinavia? No.
No questions about that.
Okay.
But a question, for example, if you do some nice modeling, there's a nice software console.
Yes. That's multi-physics.
Yeah, I know.
Yeah.
But then you get a really nice force. I mean, the entire force field inside the element, and the customers, they are not interested in looking at the field inside the elements.
No, because what they need is, you don't need to make a 3D fine element mesh model for a concrete wall. It's so standardized and it takes way too much time to do it in detail. But if you want to research exactly what's going on around the reinforcement bar, the angles, and right in this area, you need like software like this. But FEM-design is like, it's practical software.
Because if I want to optimize, if I'm a manufacturer of concrete elements, then I would be really interested to see the actual forces inside the elements when they are inside a building.
Yes, but this is also what you get here. We have shell elements in our model, and normally I've not seen a wall model with 3D fine elements because it's extremely heavy. It can calculate for days. So it's not really a practical solution. Before they start to use the graphic card and parallel programming, then something might happen there. But at the moment, it's not really a solution for a whole building.
But do you have any plans of being able to do that?
I have many plans.
Yeah?
Let's see. We have our 3D fine element mesh now in the soil with plastic behavior of more column. So that was a big step for us. The next step could be to implement it into our plate and wall regions. Okay. You never know.
That's really nice. What kind of meshes are you using for these ground metal? Are you using regular meshes or?
I remember we have 27 nodes in one element. I don't remember what it's called. Hexa. I don't remember what it's called.
Well, looking forward to see some nice force field modeling.
Yes.
How do you work with the IFC import model? Because I tried to export an IFC model from PRE-FAB and import it to FEM-design, but it doesn't work because it's not a structural members. How do you?
Exactly. Take it through Revit.
How do you see future for IFC import?
Yeah. It has a lot of. It's difficult with IFC. Because it works a little like Google Translate. Still. On Desi's beautiful diagram with the baby and the teenager, I'm not sure if IFC is between the baby and the teenager now or what it is. But of course, it's growing and growing. It's the open source we have. That's the only one. So it will be more and more. And actually, 5 years ago in FEM-design, we also have SAFE as IFC and Open IFC. We believed in it so much. But we were just ahead, so we actually scaled it down and moved our focus on the BIM focus to Tekla and Revit connection. So if you like, right now you can solve it with a workaround, open it in Revit and send it to FEM-design. This is the only way we can do it now that really works. But some models in IFC works for some reason, some do not. So the schema in IFC must be real exact for FEM-design to understand it. So. No more questions. This is your chance. Okay. Thank you for listening.